In this section, I would like to talk about a very important applications of the MOS capacitor before going to the MOSFETs. We have introduced in part 1 how to use a PN junction to detect optical signals. However, converting an optical signal into an instantaneous current is subject to noise and delay. For applications like digital cameras, the diode current is usually integrated over a short period of time, and the collected charge is used to represent the light intensity. The sampling principle is also used in conventional photography by using the shutter speed to determine the period of optical signal integration. Using what we have learned before, this optical signal integration can be achieved by connecting a PN junction diode to a capacitor where the current is integrated over a known period of time to gather the total charge. The combination of a capacitor and a diode in a more compact form is just a MOS capacitor. Operating a MOS capacitor as a device to manipulate charges is called a charge-coupled device, or CCD for short. It is a very important invention for modern digital cameras that the inventors, Willard Boyle and George Smith of Bell Labs, were awarded the Nobel Prize in Physics in 2009. A CCD is just an MOS capacitor, but it is operated in a deep depletion mode. When a fast pulse with a voltage amplitude larger than Vt is applied to the gate, the generation cannot provide the electrons required to achieve the equilibrium immediately. Without the inversion electrons, the situation is considered to be an extension of the depletion case, and the depletion width extends beyond XD-max. Instantaneously, the surface potential phi s is given by the potential divider circuit between the gate oxide capacitor and the silicon depletion capacitor. This is a non-equilibrium situation, with the energy band bending more than what it is supposed to. If you wait long enough time, electrons will be generated, and phi s will eventually become 2 phi b in the equilibrium condition. This has been explained before, and nothing new is introduced here. The difference between the initial surface potential and the final surface potential is called a potential well or a quantum well. You may simply consider a quantum well as a container of charges. When it is empty, the depth of the well is equal to the initial phi s after applying the Vg pulse minus 2 phi b. When electrons are generated, you may view the quantum well as a water-containing well being gradually filled by underground water, and its clearance depth gradually decreases. Eventually, the quantum well is completely filled, and the band bending reaches the equilibrium value of 2 phi b. And the amount of charge to completely fill the quantum well is given by Cox times Vg minus Vt. This is the equilibrium value of inversion electron charge for a given Vg. Between the cases when the well is empty and full, different amounts of electrons are being stored in the well. For a short period, say 20 microseconds after a fast pulse is applied to the gate, we can assume the well to be empty, as the generation rate is in the millisecond range. This is very slow compared with a period of 20 microseconds. In this period, if we shine light to the capacitor, electron-hole pairs will be generated. Electrons will be collected in the well by the electric field from the gate voltage, and holes are driven away to the ground at the body contact and removed. The amount of electrons collected in the well will be proportional to the intensity and duration of light shined onto it. By measuring the stored charge, we can find out the intensity of light shined onto the device. This charge has to be read quickly in the microsecond range so that the thermal generation process will not add any generated electrons to it.